All right, hello everyone. Welcome to my channel. This is a channel that is designed to educate you on uh, some great theories of everything that I think would help you out in your life, help you with your paradigm shifting and your holistic worldview um, formation. And maybe even help you to create an ingenious device that would help humanity in general. And today is our 380th video on Dewey B. Larson and his reciprocal system of theory. And Mr. Larson was born in 1898. Around 1930, he was working on, he was an engineer, and he was working on a kind of a chemistry problem, trying to figure out the interatomic distance of different elements based on the numbers on the periodic table. And he had a few epiphanies that showed him that led him to conclusions that were much broader than that. And so he did a complete study on it, and eventually in 1959 put out his two fundamental postulates about the nature of this universe. And then from those postulates, he went through a process of deduction, which I documented in about 15 videos that I did about a year ago. If you want to go back to the outline of the deductive development of the reciprocal system. And he derived, through that deduction process, a theoretical universe about what his universe would look like if his postulates were true. And then he set out in his books to kind of compare his theoretical universe with that not so theoretical universe, the empirical universe that the scientists had arrived at through measurement and observation, and putting down in the scientific tables and so on. And all that is very much worth looking at. So we're trying to look at that in these videos. Larson's theory is very difficult to understand. Mostly because you have to unlearn certain things that you already learned. Also, he's just one individual doing a Herculean task and trying to come up with a language, a new language for things that haven't been described yet. And so it's not always going to be smooth sailing. Whenever you're the originator of a theory, you have to, describe things that other people have not ever described before. And so there's a lot of resistance to Larson's theory, but I think the fact that he's able to derive a theoretical universe that closely resembles the actual universe, so-called, the empirical universe, and that he's able to make several predictions about things in the future that hadn't been discovered yet, such as quasars, that his theory deserves a hearing. And so we're trying to give it a proper hearing here. I can't claim to be any type of expert on this. I've read all of Larson's books, I believe, but I can't say that I've understood them. I understand bits and pieces, and I'm pretty, bulldoggish, about taking notes and going back and trying to re-understand it and going back and going back and going back. But I'm a liberal arts person. I'm a historian, and so sometimes the abstractions and the complex mathematics. Most of it isn't really complex mathematics, though. But just kind of the abstract thinking sometimes leaves me behind. And Larson, I believe, is a very good writer, but he's not a great teacher. He doesn't, and again, it could be a lot of it because he's just trying to do the best he can with the resources that he has and the time that he has. And, sometimes you have to dig out the nuggets that are buried within some paragraph, obscure paragraph. He doesn't have the whole thing, on a silver platter for you, we'll say. That's where I think I can come in, and other people on this channel, perhaps, that we could really put this on a silver platter for people in the form of like a textbook or something like that, where it's right there and it's all organized and it's really easy to grasp. I mean, it's never going to be easy, but I think a high school chemistry equivalent class could be organized that that you go through this textbook and that you work on it 50 minutes a day for 5 days a week, and you can get it in a semester or two. Anyway, the basic gist of Larson's theory is that we don't live in a universe of matter. We don't live in a universe of energy or a universe of force or anything else, but we live in a universe of motion. And for Larson, motion was a relationship between space and time that sets up a generalized reciprocal relationship between space and time. That means that space and time are identical to each other, except that they are reciprocals. They are in a different order, they're fractions. And therefore, whatever qualities one has, the other also has. And that space and time don't exist separately, they only exist together in motion. And so one thing he was able to observe about space is that space is three-dimensional, XYZ coordinates, stationary space. Larson calls that coordinate space. And so therefore there is also three-dimensional time, coordinate time, still in time, and coordinates. Now, that doesn't mean that a direction in space is equal to a direction in time, but it means that there are three dimensions of time. What those dimensions are is a different question, and that what we observe about time is that time is always getting later and later and later and later. And so therefore there's an aspect of space that's always getting later and later and later, or the equivalent of that. And that is in space, space is always getting farther and farther and farther apart. Larson refers to this as clock time and clock space. And this is more fundamental in that it is a scalar motion. It's a motion that has a magnitude, but it doesn't have a specific direction. The clock isn't moving in a specific direction other than later and later and later. You can't say that it's moving south or 90 degrees offset from where it was moving before. And so too with space, and you can envision this in space using a balloon with dots on it. If you blow up the balloon, all of the dots are moving away from each other, and every dot is moving away from every other dot. The farther away they are, the faster they're moving away from each other, but they are not moving in any specific direction. That is a scalar motion in space. That's what Larson calls clock space. And that has actually been observed by the legacy scientists through their telescopes, that all of the distant galaxies are moving away from each other. Also, time and space only exist in discrete units. There has to be a full unit of space and or a full unit of time for you to have space or time. Motion as well. Now, motion is basically a fraction with space or time as the numerator and time or space as the denominator. All of our scientific quantities have space, time, fraction coordinates, such as speed. The car is moving 5 miles an hour. 5 miles of space in 1 hour of time. Space over time, speed. Acceleration is space over time to the second power. I dropped the ball out of the window and it fell at 32 feet per second. 32 feet of space and 1 second per second of time. Space over time squared. And the inverse of the speed is energy. Energy is time over space. It took me 3 hours to push that thing half a mile. 3 hours of time and 1/2 hour of space. And you can see also the reciprocal relation built into that. The car is moving 5 miles an hour. You can say, well, why don't we double the speed? If you double the speed, you can say, then now the car is moving 10 miles per hour. 10 miles of space in 1 hour of time. You multiply the space by 2. But you can equivalently just divide the time by 2. The car is now moving 5 miles per half hour. That is the equivalent of 10 miles per hour. So you can see that reciprocal relation there in speed. That relation obtains in all other configurations of space and time as well. Now, what you can now when you use that discrete unit postulate, that's time and space come in discrete units only. If you have 1 unit of space in 1 unit of time, speed, space over time, then you have the speed of light. So the speed of light is 1 over 1 equals 1. Larson calls that unit speed. The speed of light is unit speed, and it is always existing. This is the background speed of this universe of motion, or it is the ether, or the origin, or the 0 point, the null point, the neutral point, the reference point. The progression of the natural reference system is what that speed of light outward in all directions. So this is a scalar motion at the speed of light. And that is always present. When you have nothingness, when you have total nothingness, that's what you have, the speed of light outward in all directions. Of course, that flies in the face of legacy scientists who make their measurements from 0 speed. Larson makes his measurements from that unit speed. And that also sets up 2 sectors of the universe. One sector is moving slower than the speed of light, and one sector is moving faster than the speed of light. The faster than light speed sector he calls the cosmic sector. The other he calls the material sector. Again, that flies in the face of legacy scientists like Einstein, who says that the speed of light is the maximum speed of the universe, when actually the speed of light is the midpoint of the universe, and an entire half of the universe is moving faster than the speed of light, which the legacy scientists deny. But they could catch up quickly, because what's going on in the material sector is identical to what's going on in the cosmic sector, except that the roles of space and time are reversed. So in the material sector, you have relations based on coordinate space, 3 dimensions of stationary space, and clock time. The clock is always getting later and later and later. So once you cross that speed of light boundary, that unit speed boundary, then you move into the cosmic sector and you get relations that are based on coordinate time, 3 dimensions of stationary time, and clock space. Space is always getting farther and farther apart. So that shows you a little bit about how the system works. Now, today we are looking at an article that Larson wrote, and it's mainly like history of science. It's called Just What Do We Really Know? And this is the second installment. So the first installment I did yesterday, and in that first installment, Larson talks a lot about how scientists, especially the front rank top scientists in the field, especially in the theoretical field, admit that they really don't know what they're talking about, and that they are in desperate need of a generalized theory to cover everything. But they despair that such a thing might not exist. But, he quotes all kinds of the greats, Bridgman and Heisenberg and Schrödinger, and they all, admit that, we don't have that overarching theory that is going to glue all this stuff together. And so, we don't really know what we're talking about. So this is the second installment. So we're just going to go from here, in the words of Mr. Larson. The objective of this memorandum is to bring out that under present conditions, the scientific profession cannot afford to rely on this indefinite someone to put its theoretical house in order. The situation is too acute for that. These pages will emphasize the astounding degree to which general acceptance has been substituted for proof in current scientific practice, and the almost incredible number of non-factual items which are masquerading as established facts. Obviously, the new and better theory, which is so greatly desired, cannot be erected on any such dubious foundation. But if the debris is to be cleared away, it will be necessary for the individual scientist to take a hand in the matter and arrive at his own conclusions, rather than to assume that someone will do it for him. It is not difficult for anyone to see how much of the scientific knowledge of the present day is merely pseudo-knowledge once an effort is made to look the situation squarely in the face. Let us begin by pointing out that extrapolations from established facts do not constitute knowledge. A substantial part of what now passes for knowledge in scientific circles actually consists of extrapolations from observed facts rather than the true factual material. As Bridgman once observed, many of these are perfectly hair-raising extrapolations. A good example is the almost universal belief that we now know the nature of the processes which furnish the energy supply for stars. Even in a day when hair-raising extrapolations are somewhat commonplace, this one sets some kind of a record. In view of the gigantic extrapolation that is required to pass from the relatively insignificant temperatures and pressures obtainable on Earth to the immensely greater magnitudes which we believe, also through extrapolation, exists in the stellar interiors, even the thought that the answers might be correct calls for the exercise of no small degree of faith in the validity of our processes. Any contention that the extrapolated results constitute actual knowledge is simply ridiculous. To make matters worse, this is not merely an extrapolation. It also involves the assumption that the isotope of hydrogen, which is stable under terrestrial conditions, will become unstable under stellar conditions, an assumption that has no factual support. It is popularly believed that the hypothetical hydrogen to helium conversion process attributed to stars is simply another atomic bomb type of reaction. We often hear the statement that in using atomic power, we are drawing on energy from the same source utilized by the stars. The truth is, however, that all of our known atomic energy producing processes depend on the existence of unstable isotopes that will ultimately disintegrate of their own accord, with the production of just as much energy if we let them follow their own course. All that we actually accomplish is to increase the rate of disintegration. The hypothetical conversion of the H1 isotope to helium is not another process of this same kind. It is a process that does not take place spontaneously on Earth or anywhere else that we know of. Many atomic reactions which do not occur naturally, including this hydrogen to helium reaction, can be forced to take place under appropriate conditions. Small-scale experiments in the laboratories have indicated that some of these reactions are exothermic, or perhaps we should say exoergic, to be more general. From this, the conclusion has been drawn that if the temperature is raised high enough, the kinetic energy of the atoms themselves will be sufficient to ignite a fusion reaction that will be self-sustaining. This sounds very plausible, to be sure, especially since we are accustomed to thinking of atomic reactions in terms of an analogy with combustion. But if we examine the conclusion carefully, it is apparent that it involves the assumption that an exothermic process is a naturally occurring process, and we know that this is not always true. If it were, we would not need atomic power. We could meet, it says beat, but we could meet our power requirements by desalting seawater. The currently popular theory of stellar energy generation is therefore not only a hair-raising extrapolation, it is also based on a very questionable assumption. So far as the objective of this present memorandum is concerned, it is sufficient to show that the accepted ideas as to the nature of the stellar energy process are not necessarily true, and that treating them as established facts is totally unjustified. It may be mentioned in passing, however, that there are actually several items of evidence which indicate that these areas are not only open to question, but are completely erroneous. For instance, it is a general rule in the laboratory experiments involving high energy impacts that the degree of fragmentation becomes greater as the incident energy increases. If this rule holds good at stellar temperatures and pressures, and we have no reason to think otherwise, it favors the existence of hydrogen atoms rather than helium atoms. Even the combustion analogy suggests the same conclusion. Extremely high temperatures do not favor exothermic chemical combinations. On the contrary, they dissociate the combinations that already exist. Furthermore, the hypothesis of a self-sustaining hydrogen reaction ignited by high temperature in a body consisting primarily of hydrogen introduces a problem of control for which there seems to be no answer. The steady and relatively slow generation of energy, which we actually observe in most stars, requires some kind of a definite limitation on the energy supply or on the process itself, which is wholly incompatible with current concepts. Other lines of reasoning based on such evidence as the ratio of hydrogen to helium in the cosmic rays and many observed facts from the astronomical field lead to similar conclusions. Conclusions based on extrapolations are not knowledge. If a physical theory that has been generally accepted on the strength of faulty or inadequate evidence is actually valid in spite of these deficiencies, as we can expect will frequently be true, no harm has been done. On the other hand, if such a theory is not valid, the bad effects are not necessarily confined to the area directly affected. They may be multiplied manifold by the use of the original erroneous conclusion as a base for the erection of additional theories. A mistaken idea as to the source of the energy of the stars is not too serious in itself, but as it happens, the whole structure of stellar energy generation process, the whole structure of stellar evolutionary theory has been based on this assumption as to the nature of the stellar energy generation process, and the net result has been a serious distortion of the entire astronomical picture. The astronomer does his work under rather severe handicaps. He cannot experiment. All that he can do is to observe. Furthermore, the range of conditions within his field of observation is so much greater than the range existing on Earth that much of what he observes can be related to familiar phenomena only by long extrapolations. And these, as has been brought out, are always subject to serious question as to their validity. Then also, the astronomer is, for the most part, limited to what is essentially an instantaneous picture, even though it encompasses a wide expanse of time as well as space. He sees astronomical objects in what are apparently various stages of evolution, but he cannot determine the direction of evolution from direct observation. He must draw his conclusions on this point from collateral evidence of some kind. In addition to these inherent and unavoidable handicaps of his profession, the astronomer has voluntarily accepted a blind and unquestioning faith in the conclusions of the physicists with respect to the stellar energy process. Okay, we're going to stop it right there and move on to the next section tomorrow when we meet again. And I don't know how long this article is. I believe it will go on for a few days here. And but that was second installment of Dewey Larson's How Much Do We Really Know? And he's tackling the astronomical situation, the generation of energy in stars primarily. And a lot of that comes from his book, Universe of Motion. So if you want to take a look at that one, it's part of his 3-volume Structure of the Physical Universe, edition 2. And anyway, but we will get back into that tomorrow. Thanks for tuning in today, and have a great day.